Good afternoon, everybody. My name's Robert Parker. I'm Chief Executive of the Royal Society of Chemistry next door, and it's my great pleasure to welcome you on behalf of the Geological Society of London and the Royal Society of Chemistry. This is a joint public lecture celebrating the Geological Society's Year of Carbon and the United Nations International Year of the Periodic Table. The RSC and the Geological Society have been courtyard neighbours for many years, since 1874, and our two organisations are very pleased to collaborate again with the aim of making science more accessible to the public. Together with other courtyard societies, the Linnean Society, the Royal Astronomical Society, the Society of Antiquaries, and the Royal Academy of Arts, we represent a broad range of arts and sciences, working for the public benefit in a vast number of ways, from informing government policy to supporting teachers and students in the UK and around the world, and of course welcoming members of the public into our historic premises for events such as these. So 2019, the year of the periodic table, marks the 150th anniversary of the Mendeleev periodic table, which is an iconic image and a vital tool to all who learn and work in science at all stages of their learning and careers. The RSC and its members are leading the UK's contribution to this international celebration, including supporting hundreds of outreach and educational activities and other initiatives throughout the year. We're also halfway through, or a bit more than halfway through, the Geological Society's Earth Science Week, an international celebration of the geology all around us. Here in Burlington House, you can see the winning photographs from this year's Earth Science Week photo competition. You can pick yourself up a pet rock. I'm quite jealous because we don't have those next door, and see the new collection of mineral hand specimens on display. So do check those things out. And follow International Year of Periodic Table and Earth Week on social media. And so moving on from that, I'm very happy to introduce your guest speaker for today, Professor Ros Rickaby, to explain what made the ocean turn red 200 million years ago. Ros is Professor of Biogeochemistry in the Department of Earth Sciences at the University of Oxford. She received her PhD from Cambridge University in 1995 and studied at Harvard for a postdoc with Dan Schrag. Her research aims to develop ways to reconstruct and understand the co-evolution of life and Earth's climate. Please join me in welcoming Ros to the stage. Thank you.
Good afternoon. It's a pleasure to see so many here, and I'm afraid I've taken the liberty of slightly updating my title, perhaps to speak more to the general theme of the lecture. But I will still talk about what made the oceans turn red 200 million years ago. But I thought I would start out with the sort of more general question of what on earth the periodic table got to do with plankton. And so this is the world of plankton that I work on. These fabulous single-celled organisms don't work so much on this one, but it's kind of fun to watch. So these are these fabulous single-celled organisms. I'm particularly interested in these guys because they photosynthesize, so they fix carbon into their squidgy organic parts of the cell, but they also generate these calcium carbonate platelets in these fabulously intricate patterns. And that actually has big implications for the carbon cycle in the ocean and the scale at which carbon is pumped into the deep ocean. This is just a satellite image of a bloom of these coccolithophores where we're picking up the reflected light from the calcite of each of these things. Even though they're a micron in size or micron scale in size, we can pick them up by satellite imagery. So they have a big impact on the Earth system. So this is just to try and put them in the context of carbon dioxide and carbon dioxide change since the 1880s, looking up to the year 2015. In the grey and the brown, what I'm showing you is the CO2 flux that's come associated with fossil fuels and industry, this rising trend of carbon dioxide being emitted from the burning of fossil fuels and associated with land use change. But there is a destiny to that carbon dioxide. So some of it has gone into the land sink. So we can see that fortunately the land sink, i.e. the fixing of carbon into terrestrial or plants on land and into soils, has increased at the same time as CO2 has gone up. This pale blue is showing us the accumulation of carbon dioxide in the atmosphere, which is associated, of course, with greenhouse warming. But then we have the oceanic sink, which accounts for about a third of this emission of CO2. And that oceanic sink is partly to do with solubility. So as we have more carbon dioxide in the atmosphere, more CO2 equilibrates with the surface waters and is drawn down into this ocean sink. But a major additional factor is the biota that is existing in the ocean. Just to try and put a sort of scale on this, so you can see here that the ocean is responsible for sinking about 10 gigatons of CO2 per year. Just to put that in context, that's the same as about 3 petagrams of carbon per year overall, the net oceanic sink. So if we then look to the plankton that I'm so interested in, they exist in the sunlit surface waters up here. Sorry, this is maybe a little bit more complicated than it need be. But ultimately, they undergo photosynthesis, so they take carbon dioxide, which is equilibrating with the atmosphere. They fix it into their squidgy organic parts. And then those squidgy organic parts ultimately go down into the deep ocean via this organic carbon export. And our best numbers give us an idea that in the surface waters, I've lost my pointer. I don't know if I've got another one, sorry. No, it's gone. Okay. In the surface waters, we produce about 47.5 petagrams of carbon per year in terms of that's how much actually goes into the plankton. There is some cycling of that carbon that occurs in the surface waters associated with bacterial remineralization, but we have an export on the scale of 5 to 13 petagrams of carbon per year. So what I'm trying to point out is that this biotic pump of carbon today is of the same order of magnitude as our emissions of CO2 into the atmosphere. So this is an incredibly powerful pump of carbon into the deep ocean. It doesn't all stay there. Some of it gets re-upwelled and will re-equilibrate with the atmosphere, but it's a major flux of carbon on the surface of the planet. This biological pump, if we look in the top 2 panels here, we're looking at chlorophyll. This is part of the chloroplast that is helping the organisms absorb light and undergo photosynthesis. And you can see, again, this is right up there in the photic zone. In the right-hand panel, we're looking at incident radiation. And the point that I'm trying to make here is that as those phytoplankton photosynthesize, they take out nutrients. And that's shown by this nitrate concentration here. Ah, fab. Okay, no, that's fine. I'll switch it around. Okay, so here we've got the nitrate concentration. The blue colours are showing you very low nitrate concentrations, going down to about 0. So as life is living in the ocean, it's using up these nutrients and depleting them in the surface, leaving those nutrients very depleted. But as it remineralizes at depth, those nutrients get replenished into the water, and so you have high nitrate in deep waters, low nitrate in surface waters. And this is the working of the biological pump, taking carbon, nitrogen, and phosphorus from the surface waters into depth. At the same time, just to point out, this will become important a little bit later, as we remineralize or respire that organic carbon, we also use up oxygen in the deep water. So oxygen is depleted or lowered in the deep water. Here it's not going very low. We've still got about 190 micromoles per kilogram. But I'll show you later that in some parts of the ocean, the oxygen is very much lower than that. But if we look across the entire globe and we think about the efficiency of the biological pump, this is looking at a map of sea surface nitrate across the ocean, and these purpley blue colours are showing very low nitrate concentrations, as we might expect associated with the biological pump. But there are some parts of the ocean, notably around here, around the Southern Ocean, around Antarctica, up here in the subarctic Pacific, and in some parts of the eastern equatorial Pacific, where there's a bit of nitrate left. We've got nitrate going up to quite high concentrations down here around Antarctica and up in the subarctic Pacific. So there's this real question of kind of why is the biological pump not working so efficiently in these parts of the ocean? It seems to be very good at taking out all the nitrate here in these lower latitude areas, but in the high latitudes there are nutrients that are left in the water column. So something else, it would appear, is limiting the biological pump in those waters. And John Martin, in about the 1990s, was the ideal guy who was able to suggest that actually the nutrient that is missing, that's not available for phytoplankton in those waters, is iron. And this has garnered an enormous amount of interest in iron and its interactions with phytoplankton, to the point that people have been testing whether phytoplankton in the ocean are limited by iron in these areas where we've got excess nitrate left in the surface waters. And this is a really nice satellite image of an experiment where iron was put into the surface ocean. It engendered a bloom of diatoms here, these fabulous silicious phytoplankton, and their chlorophyll was captured by a satellite image about 40 days after this iron fertilization experiment. And so this was evidence that if we were to go to the Southern Ocean and put iron into the ocean, it is indeed limiting phytoplankton such that giving them some more allows biological productivity to increase. And John Martin made this great statement, which was, give me half a tanker of iron and I'll give you the next ice age. And this indeed is what we found. So looking into the last a million years, as recorded in Antarctic ice cores. This is showing the glacial, interglacial oscillations of temperature. This is looking at changes in temperature here, alongside sea surface temperatures. We know from ice core bubbles that we've got carbon dioxide going down and up associated with these glacial, interglacial cycles, so lower carbon dioxide at periods of glacial temperatures, higher carbon dioxide when we've got interglacial warming. So this is the natural breathing in and out of carbon dioxide that has occurred alongside the glacial, interglacial cycles. And we can actually reconstruct the iron flux, the dust flux, into those ice cores. And you see associated with each of these periods of low carbon dioxide an increase in the flux of iron that's recorded in this ice core. So we have dustier times in the glacial periods. And if we go to marine cores, we've got, again, records of dust that go alongside these glacial, interglacial cycles, but also measures. This is looking at organic carbon accumulation rates in cores, which we can relate to primary productivity. Similarly, looking at alkanones, these are particular molecules generated by coccolithophores, and we can see that these go up and down alongside these glacial, interglacial cycles. So John Martin was essentially right. There is indeed a component in which, in a glacial atmosphere, we've got enhanced temperature gradients, faster winds. There is more iron going into the oceans, which is fertilizing productivity and contributing to that CO2 drawdown. So this really shows the power of the biological pump in moderating climate over the last million years or so. Oops. So we might now sort of take a step back and say, well, why do phytoplankton need so much iron? Why is that an element that is so important to phytoplankton? And this is where it's sort of useful to think about how they're accumulating their iron and how that iron is available to them. If we contrast plants living on land, they've got roots that are able to mine, essentially, the rocks and the bedrocks and the soil where they can absorb nutrients into the plants, and that allows them to grow. By contrast, phytoplankton, of course, are living in a rather dilute medium. They're living in an ocean. The rocks are quite a far away on the continents. And so for them, the nutrients that they require have to be soluble, have to be available in that water form. And this is just to show the abundance of elements. This is in the universe, which I'm kind of using to approximate the Earth in general. This is the abundance of elements made in stars. And this is just looking at a log of their relative abundance. And so we've got things like hydrogen and helium made very nicely in stars. And then we decrease in abundance as we go, increase across the atomic number of the elements here. And I'm just highlighting for you here that iron is in fact one of the most available or the most abundant elements that's been made in stars in the universe and is indeed highly available or highly abundant in the continental crust. We've then got a range of these other transition elements, things like nickel, manganese, zinc, copper. These are all elements which are very interesting to biology and in fact are part of the metalloproteins that biology is using to live. They're reasonably abundant in the universe. If we go into the oceans here now, this is looking at the availability of elements in the oceans, the concentration on the y-axis and the elements again going up with atomic number. You'll see that the biggest difference between the abundance in the universe and the abundance in the oceans is really in these kind of biologically interesting elements, vanadium, iron, cobalt. These all are very much lower in availability in the oceans compared to the Earth as a planet. But biology is not stupid. It's used the chemistry that is available to it. And I actually think this is kind of a really profound observation in many ways. This is a representation of the periodic table where the height of the bars represents the concentration of that element in the ocean. I've done some jiggery-pokery with logging of things in the femtomole to kilogram way to get everything such that it's a positive number and I can generate it as a column. But what I've also coloured is the bulk biological elements, so things like sodium, magnesium, potassium, calcium, carbon, nitrogen, phosphorus. This is where these elements are important for life. But also the trace elements that are believed to be essential for life. And what you should be able to see is that the elements that are essential for life are also the ones that are at the highest concentration in the ocean, by and large. So the taller the column, those are the ones that seem to be coloured in a way that life can use them. So life has essentially used the elements that are available to it. So is this kind of where the iron dependency comes from? And I guess the key thing to also think about is the fact that the chemistry of the ocean has not stayed the same throughout geological history. There has been a big change in the ocean, and in fact a number of big changes to the chemistry of the ocean. So then becomes this question, well, if life is sort of looking like the chemistry of the ocean today, has it evolved in its chemistry through time as geological, the seawater chemistry of the ocean has changed through time? And so we need to think about what the chemistry of the ocean has been in the past and what implications that had for the chemistry and for these major elements in the ocean. One of the things that we know has been a major transition in terms of chemistry is the proliferation of photosynthesis and the generation of oxygen on a planet. If we go back 3 billion years, the atmosphere was suffocating, there was minimal amounts of oxygen in the atmosphere. And cyanobacteria, I sort of like this analogy, they were the one organism before us that had the impact to change the environment such that it affected everything living on the planet. So at that point, everything was anaerobic. They essentially poisoned the atmosphere with oxygen such that things had to adapt to that change. And so there are kind of a nice analogue to our global warming where we as a single species are kind of affecting the carbon dioxide of the planet for everything living on it. So this is our record in the billions of years of looking at when oxygenation really occurred on the planet. And we have this elimination of a particular signal. We could talk about it, but basically, if you've got some oxygen in the atmosphere, then you do not see this mass-independent fractionation. So this is where the presence of oxygen has eliminated the mass-independent fractionation of sulfur. And in the older times, mass-independent fractionation is around and indeed gets preserved into the geological record. So this is really a kind of presence-absence of oxygen. And we know that there was a major oxygenation about 2.2 billion years ago. But it's quite probable that that did not reach modern-day levels of oxygenation and that there were further episodes of oxygenation. just to kind of try and put this in context, I sort of found this really nice figure that sort of puts this on a smell scale, essentially. So the various cores were taken from kind of low oxygen types of environments, and you can imagine that the modern day is kind of no smell. As you go back in time, you start to get some of these rather noxious species, hydrogen sulfide, existing, going up to quite high concentrations. And so we go down this wonderful scale of earthy, funky, not appealing pond smell. Do we have to describe it? Everybody in the building can smell this. So right back in that time, we've got this rather pungent, smelly world with lots of reduced species around. And we've evolved towards a sort of oxygenated planet, which fortunately is aroma-free. So what does this change in oxygenation do to the chemistry of the planet? Well, one of the things that changes is this thing called the redox potential. So we start to increase oxygen and we go up this thing called the oxidation potential ladder. And what that does is, as you create more oxygenation, you have a greater ability to strip electrons off elements, and that changes their speciation. So as examples of that, if we go back to this very low oxygen world, we have things like uraninite being found in the sedimentary record. So this is where uranium is existing as this uranium oxide solid in the 4+ state. As you raise oxygen, it starts to become soluble and goes into the 6+ state. You've essentially stripped electrons off uranium and it's become soluble rather than sitting in an insoluble state. So as we have this transformation, we start getting uranium becoming more and more available in the ocean, and we stop seeing uraninite in the sedimentary record. Similarly, you get detrital pyrite, so iron sulfide, so that's over here. As we start to oxygenate the planet, we start to go up this redox potential ladder, and we transform Fe2+, which would have bound with the hydrogen sulfide to create these pyrites, and these are detrital grains, so literally existing on the continents. As we increase oxygenation, we stop finding detrital pyrites. And instead, what we start to see in the geological record are these incredible banded iron formations where that iron precipitates out as an oxyhydroxide. So we go from seeing iron in a very reduced form to seeing iron in a very oxidized form. And this is the sort of geological record of changing redox potential as oxygen has increased in the atmosphere. We've essentially rusted the planet, and we have these incredible banded iron formations that build up to about 500 million years ago or so, and then they're no longer found in the geological record. So it implies that iron becomes so insoluble at that time that it never has an opportunity to build up to any great concentration in the ocean. Whoops. I will sort out my clickers. So as well as changing redox potentials and therefore changing the solubility of different elements, we also change the solubility of the sulfides to the hydroxides. So we change things to become more oxic, and we change the relative solubility of minerals. I've talked you through a little bit of that with iron sulfides and looking at uraninites. But the point being is that many of these biological elements, certainly things like copper and zinc, became much more soluble as you oxygenated the planet. So copper and zinc were locked away in very insoluble sulfides when you've got very little oxygen on the planet. But they become much more available as their hydroxides are much more soluble at higher oxygen concentrations. So we have these chemical ways of thinking about what would have happened to the chemistry of the ocean. And we can actually start to have a model for how would elements change as we go through geological time, based on our best estimates of the oxygen concentrations through time. So what I'm going to point out to you is that here is iron. This is the change of iron through time, so a distinct drop around that 2.2 billion year ago oxygenation period. And then we have a second drop around 0.5 million years ago or so. Iron has had the biggest change in its concentration. What are we talking? 5 orders of magnitude or so. So it's incredibly available in this ancient Earth and vanishingly available in the modern oxygenated Earth. Similarly, we can look at things like manganese and cobalt, and so we can see manganese has basically stayed about the same, and it's only in the last oxygenation that it actually turns from Mn2 plus to the insoluble MnO2, so where it gets to the +4 state. It's higher up that redox ladder that we looked at a couple of slides ago. Similarly, cobalt, we can see, if I just get my eye in, so here we've got cobalt declining towards the modern day, a big step at about 2.2 billion years ago, and remaining a little bit stable to the modern day. So the point being that a number of these elements have become less available to life. Molybdenum is an interesting one. It's become very much more available as we've increased oxygenation. And the same can be said for zinc and copper. Again, remember how insoluble their sulfides were. And we think that they became very much more available at this time when sulfide in the ocean really goes down to negligible levels. So there's a real picture of changing trace element chemistry in the ocean that we can predict from very simple, actually, chemical equilibria. Can we find evidence for this in the geological record? So we've looked into ancient archives of seawater chemistry. There is a sense that we can look into sediments, we can look into precipitates, chemical precipitates, these banded iron formations. We can look into black shales. We can look into pyrites, these nice framboidal, they look a bit raspberry-like. These various different deposits may well tell us about some of this chemistry through time. And indeed, this has been put together by Robbins et al. In 2016, showing, I think hopefully you'll remember, that cobalt decreased through time as we oxygenated the Earth. And indeed, the cobalt to titanium ratio of sediments through time appears to have declined, particularly around this 2.2 billion year oxygenation. The same has happened to nickel. We see declines in nickel. And if you remember, uraninite, that sedimentary particle that was going to dissolve and turn to the more soluble form, then indeed we see uraninite peaking around this 2.2 billion year oxygenation and then increasing as we go through this second step of oxygen. And again, molybdenum we see also becoming more available as you go through time with a step up around 0.5 billion years ago. So that's what happens to seawater chemistry. What about in organisms? I'm sort of here as a phytoplankton person. So what we've been doing in my lab, where there are now these fantastic techniques where we can actually look at all the proteins expressed by different organisms, and we can look for the specific metal binding centers in those proteins and start to develop a quota for those different organisms in terms of the elements that they require. And this is what we've done in this graph to the left-hand side of here. So we've looked at cyanobacteria. These are represented in, keep on losing my laser, sorry, in groups 1 to 2. And then as we go across into the green box, we're going into the green algae, and I'll show you a little bit more what those actually represent in a minute. But we're essentially going from a bacterial organism here, so something which is very uncompartmented, a very simple, small cell, to something which is much more complicated here, a eukaryote which has mitochondria, nucleus, chloroplasts. And we see distinct changes in the chemistry. We see zinc increase as we go from bacteria to eukaryotes. We see iron decrease. We see molybdenum increase, nickel decrease, cobalt decrease. All of these changes in the chemistry are exactly what you would predict as you go through this increasing oxygenation. And so it appears that the organisms are actually recording the change in chemistry of the ocean as they go from being bacteria to being eukaryotes. So across that, this has sort of interesting implications for just generally bacteria are actually surprisingly sensitive to things like zinc and copper, which were very low at the time that they were proliferating. And this means that if you sort of feel like going around your household reading the backs of things, There are antibiotic properties in this healing gel that you can get from vets for animals that you can put on wounds, and that's full of zinc, basically, because it will kill bacteria. The same is true if you look in the back. Other mouthwashes are available, but if you look in the back of the ingredients here, you'll see zinc chloride. And again, this is a sort of antibacterial agent, the same in this antiseptic healing cream. So zinc is something that bacteria were never exposed to when they were in that early stage of the planet. And as copper and zinc have become more available, they've essentially been poisoned by it. They don't know how to cope with these particular metals at high concentrations. And indeed, what's really nice is this sort of tells us actually a little bit of the history of why we tend to flip coins into water, because the release of copper actually kept water sources clean from bacteria. So there you go. When next time you're flipping into a wishing well, you can think about the co-evolution of metals and bacteria. There we go. Right. Okay. So this is just to show you then, I'm sort of trying to generate this hypothesis that the oxygenation of the planet played into this step change in the evolution of life from these simple cyanobacteria going up to eukaryotes. And the nice thing is we've now got wonderful molecules that allow us to trace the general success of the bacteria versus the eukaryotes. And indeed, it's during this period, about 850 to 500 million years ago, so just as we know that oxygen is increasing, we see all those different metals increasing in the seawater records, we also see bacteria, sort of they've gone from their dominance, and these blasted eukaryotes are starting to come in and outcompete the bacteria, and they're becoming a little bit more marginalized. And so this is really the birth of the eukaryotes being associated with this second step in oxygenation and a major change in seawater chemistry. And that has implications for the biological pump, which is where we sort of started quite a few slides ago now, that as you go from bacterial cells, these are really rather small cells that probably remain suspended in the surface ocean. The effectivity of the biological pump at that time was really rather low. These small cells don't sink. You tend to have, in bacterially dominated water bodies, you tend to have turbid conditions. Nothing is kind of sinking. It's all just staying around. And people have modeled that probably what is happening is you really have very little sinking of organic matter into the deep ocean in this bacterial world. And it's really the evolution of the eukaryotes that drives this particle sinking and scavenging and burial of organic carbon down into the deep ocean. So there was associated with this oxygenation, the bacteria to the eukaryotes, was a major change in the effectiveness of carbon sequestration into the deep ocean. So I promised I would get to why the ocean turned red. So this is the next step in this kind of evolution of the phytoplankton through time. So we're jumping forward. We've been looking at the geological record back here, going sort of 500 million or so backwards, where we've seen big changes in the eukaryotes to the bacteria to the eukaryotes. But there is a second major change in the plankton of the ocean. So the Paleozoic, up to about 250 million years ago, is dominated by green algae. We've got biomarkers for these, we've got body fossils for these. The green algae are dominating in this ocean once they've started out as the eukaryotes. But as we come into the Mesozoic times, we have a major change. And we have the takeoff of the coccolithophores, those wonderful calcitic phytoplankton. We see the diatoms coming in a bit later, and the dinoflagellates. So we have this major change in the algae that are dominating the ocean, and a big point is that they're becoming mineralized. So they're generating these shells. These organisms are also from what we call the red lineage algae. And I think I'll explain why they're called the red lineage algae in a minute. But this was a time of major change. This was essentially the establishment of the modern phytoplanktonic biota of the ocean that we have today, going from this green to the red style of ocean. And it had big implications for ocean chemistry. The fact that we generated cells that had calcium carbonate shells means that the deep oceans were coated with calcium carbonate, this kind of nice alkalinity buffer in the oceans. And this is the time where really ocean chemistry, actually in terms of carbonate chemistry, got stabilized. Because if you change the saturation state in any way, the fact that you've got calcium carbonate bathing the deep ocean here means that you can dissolve a little bit, and it will buffer out any changes to the pH that may be engendered by big volcanic eruptions or big emissions of CO2. The downside in terms of our anthropogenic change is that can take on the order of 10,000 years to dissolve it. But on geological timescales, this was the start of the buffering of ocean chemistry. So this was a major, major change. And so just to explain to you why these things are called the red algae, is in the history of algae, they've had this wonderful sort of Pac-Man stroke Russian doll type of history where I mentioned we've gone from bacterial cells to eukaryotic cells, and we know that that occurred via what we call endosymbiosis. So a little cyanobacteria was sitting around minding its own business. It got chomped by some heterotroph, and then this poor cyanobacteria essentially got enslaved by the heterotroph. A lot of its genes got taken over by the heterotroph, but it became this nice photosynthesizing cell. That photosynthesizing cell then evolved into these 3 different lineages, which includes the red algae, the glaucophytes, and the green algae. This is the guy that actually goes on to make the land plants ultimately. But this poor red algae has further excitement in store. It gets munched by another heterotroph. So you've got this kind of what we call secondary endosymbiosis. It's been basically taken into a heterotroph a couple of times, and it means that you've got 4 membranes going around the chloroplast here. But it was algae from this secondary endosymbiosis that really flourished at that time, 200 million years ago, and took over our ocean. These heterokonts include the diatoms and the dinoflagellates here, and the haptophytes are the sort of origin of the coccolithophores. So it's these this is why I call them the red algae, is this lineage of algae that have a particular set of pigments in them. So can we say anything about this from the metals perspective? And I've been involved in a bit of work that's actually shown that around 200 million years ago, there was an additional sort of oxygenation of the water column, we think related to a sort of deepening of where we get oxygen minimum zone waters. And so I was curious to see if I could see any signal of oxygenation in the metals that go as we go from primary endosymbionts to secondary endosymbionts. And these are in this blue triangle here. Triangle, square, or rectangle. Sorry, gosh, can't even identify my shape, sorry. And what we see, looking at the metals again, these are what we're getting from looking at the entire proteome and working out what the metals associated with those organisms are, is that actually, so iron goes down, so yes, that could be an oxygenation type of related thing. We know iron goes down, becomes more rusty, the more oxygen you have. Manganese goes down, again, that could be an oxygenation-related signal. Manganese goes from Mn2 plus to MnO2, so yes, solubility could be controlling these 2 things. But things start to go awry when we think about molybdenum. Molybdenum goes down as we go into these secondary endosymbiotic organisms, and we'd expect molybdenum, if anything, to go up. It becomes more and more available as you have more oxygen on the planet. Cobalt goes down, so it's really not related to oxygenation, but what seems to be happening during this secondary endosymbiosis is really a reduction of requirement for metals. These organisms are getting to the point where they don't need so much metal to exist. They've figured out ways of becoming much more metal lean. And indeed, this plays out. We can see this in the modern physiology of these things. Here we're just looking at their sort of growth rate relative to their maximum growth rate versus the concentrations here of iron and the concentrations of manganese. And the red, the purple, and the orange, I think, are these secondary endosymbiotic red lineage algae. And we see that they're able to reach their maximum growth rate at much lower concentrations of iron compared to some of these other older lineages, shall we say. And the same is true for manganese. We can see that manganese, these guys are the coccolithophores up here, and they really show no limitation at all. They're sort of always growing at maximum growth rate, regardless of how much manganese is there. So these are very metal-lean organisms. Why are they metal lean? What's the sort of driving force for them to become so metal lean at this time? And it's probably, it's this curious thing of evolution where they've sort of undone themselves. By being very good at calcifying, they've made themselves very heavy particles. And we know that the amount of organic carbon that fluxes out of that surface water into the deep ocean is related to the amount of calcium carbonate you've got in that population of phytoplankton. The more calcium carbonate, the more you're going to export organic carbon. It makes you more efficient at pulling organic carbon out of the surface waters. It's also true for the opal flux as well. The more silica, the more carbon gets exported. So the heavier you are, the better you are at pulling organic carbon out of the surface waters. And that has implications. That has implications for deepening of what we call the oxygen minimum zone. So this is oxygen concentration here, and as you increase what we call the ballast of your marine snow, you deepen this point of regeneration of nutrients and also your consumption of oxygen. And so you would be more effective at exporting your micronutrients, your trace elements, down into the deep waters. And not only that, but as you deepen the oxygen minimum zones, what we also know is that where oxygen minimum zones, this is sort of just looking at a little profile across the Peru margin. So here you can see the purple is picking out where the oxygen minimum zone is. And of course, where you've got low oxygen, iron becomes soluble, and we can see this in the iron here. So iron is soluble in those low oxygen waters. So where we've got the red colours, we're re-releasing iron from these sediments and organic carbon back into the water column. If we go through this process of deepening of the oxygen minimum zones, we stop that replenishment of nutrients back into the photic zone, where the organisms are living. So overall, as we go through this deepening of the biological pump, we increasingly limit the organisms for their access to the trace metals, and we indeed limit that replenishment that we might have had from low oxygen waters back to surface waters. And so this has forced this kind of nutrient-lean type of life or makeup of the metalloproteome. Just an interesting aside that as organisms, as my little coccolithophores, become more nutrient depleted, there's been some wonderful work here by Keano and Shiraiwa that have shown if you start to limit these coccolithophores in terms of phosphate or in terms of any nutrients, they calcify more. So it could be that there's some link between this nutrient depletion and this increase in calcification that occurs. And could this have been actually part of the trigger for becoming mineralized? There's this incredible sort of positive feedback between getting bigger, sinking more, driving lower oxygen minimum zones, driving nutrient depletion, perhaps driving calcification, sinking even deeper. So there's an incredible positive feedback at this time. And this is just showing sort of low metal strategies, again, of calcifiers. I think just in the interest of time, I'm going to sort of flip through just to point out that iron really is, I showed you the magnitude of change in iron availability that occurred associated with oxygenation. And we've been looking at sort of trying to find the number of transporters for iron in our phytoplankton compared to their requirement for iron. And it's the one element where we find this kind of inverse relationship that as organisms have increased their number of iron transporters through time, this is going from the cyanobacteria here up through our green algae and then through to our secondary endosymbionts. At the same time, they've been sort of trying to get more and more iron, as the proportion of their proteome which uses iron has declined. And this is the only element we can find evidence for this essentially harder attempt to get hold of iron and trying to slim down their iron requirement at the same time. And so I think really iron is this incredible limiting nutrient because they had this luxurious ability to use it back in the anoxic world. And it's really sort of gone away from them without their kind of control. Okay, so I just think that I'll leave you with a kind of final thing that I've tried to bring out a little bit in this lecture, which is I think there's this really interesting trend in evolution, partly by this generation of oxygen. The cyanobacteria kind of didn't really want to get oxygen. What they wanted to get was the energy from sunlight, and it just so happened that oxygen was a byproduct of that. But there's this kind of continual cycle of life challenging itself in this kind of, it creates an environment, it's doing great, but then it impacts the environment in such a way that it's more challenging. The oxygen was challenging for the life that was there on the planet. This depletion of nutrients is challenging for the organisms that are living in the ocean. But that sort of unwittingly yields a driving force for advance, I guess, that this is how evolution has worked, these challenging times, but then, okay, there's a way of figuring out a strategy to overcome that. And I guess that's perhaps a nice lesson for us with our kind of facing our challenge of global warming as we are today. So those are my conclusions. I think I've sort of said them enough, but I'll leave them up for you to peruse, and I'll take any questions.
Thanks. Do we have any questions? Oh, gosh, wherever our microphone's gone. Sorry, from the front. And Megan, can you Thanks. We'll just do that for now.
Okay, I can shout. Two, if possible. Are you saying that essentially life evolves to use the minerals that are available, and on other planets with different minerals available in different amounts, you could get different kinds of life evolving? And secondly, if iron fertilization of the ocean seems to increase productivity, does that have any possible impact on what we can do about global warming and getting rid of excess carbon? Are the fluxes good enough?
Okay, I'll deal with the second one first because it's easier. So there are indeed ideas to go out and fertilise the ocean with iron as a way of solving current global warming. I think the big challenge for doing that is looking at the oxygen balance. If we were to massively increase the amount of productivity in the ocean, then we will almost certainly drive lower oxygen in the deep ocean. Lower oxygen in the deep ocean is something that we're concerned about anyway, because oxygen has a solubility in the ocean which is decreases with rising temperature. And so we already see evidence for those oxygen minimum zones starting to expand, and they really are areas where aerobic organisms cannot persist. So I think there is a big concern for the general ecosystem at large for doing iron fertilization as a way of solving global warming. Okay, so on to the second part about life on other planets. I guess I think there is some, I guess okay, so I'm trying to work out how to frame what I want to say. But in terms of our planet, I think there's a certain inevitability to the chemistry that life has settled on, in the sense that it is driven by the availability of elements on the planet, it's driven by their solubility into water, and generally you would think that life is going to exist in water. And so I think there is an inevitability to that pattern and to that progress in use of elements. I'm trying to think on exoplanets. If you've got a rocky planet with water, then I guess it depends on the star that ultimately that planet came from, as to whether, if it was a rocky planet that had a rather similar chemical makeup to our own, I would predict that you would get the same sequence. I mean, I remember having a discussion about whether you could have a silicon-based form of life. You know, silicon just sits beneath carbon, and so you might expect that it would have the same ability to generate bonds. The challenge of that is that I think I'm right in saying, I'm trying to remember, it comes down to the bond energies, and the silicon-silicon bond doesn't have as much energy in it as the carbon-carbon bond, and so there is a really good reason why we have carbon being the main polymers of life. So sorry, that was a sort of roundabout way to say I probably don't know, but I think if it's a rocky planet with water, you would expect there to be a certain progression to that chemistry.
Is there a question back?
Thank you for a wonderful talk. Does our star, the sun, produce iron?
Oh gosh, this is getting into, hang on, I spoke to an astrobiologist earlier. Yeah, I mean, no, it doesn't. It's a hydrogen and helium burning star, right? Yes.
At the moment, it's only producing, it's not producing any of those things. It's only later that the CNO that's being produced gets out.
Okay.
And the slide you showed earlier of the cosmic abundances, that is probably the best argument against a silica light form, because CNO are the most common
Yes.
elements.
Yes.
And so any planet is probably going to be mostly CNO.
Yep.
And it's the other way around. The star doesn't produce the planets. They presumably form at the same time as the star.
Yep. Thank you for bailing me out. I'm trying to do proteins these days. It's kind of hard to do astrobiology as well.
Thank you for a very, very nice talk. It's food for thought from the CO2 ratios. For me, possibly the role of fish and the food chain, onto blood and iron again. But one I was thinking about is that the globe has been changing its oceans all over the place as you've got tectonic movements, so that certain oceans weren't there 500 million years ago, and so on. You didn't give a hint of any of that. I'm not sure whether it's relevant or not.
I think it is relevant, actually, because you would imagine that you could get some quite different chemistries if you have some quite restricted parts of the ocean where the exchange of waters can be rather limited. Places like the Black Sea, for example, today, you get very unusual chemistries there. But I think I would potentially think about those as anoxic, suboxic refugia. You know, really, when you're moving the plates around and changing the makeup of the oceans, you could be changing quite distinctly the ventilation of the oceans, and in the way that the main way that you get oxygen into the deep oceans is it dissolves in the colder water at the high latitudes, and then it gets ventilated down into the deep oceans. So I think that you're absolutely right that moving plates around will potentially change those circulation patterns, so change where you get things being more oxygenated, less oxygenated, and you may have restrictions which give you anoxia, but my sense is that those provide the refugia for the things that were there before. You know, if you've got an anoxic biota, it needs to sort of scuttle back to where those conditions prevail, be it in an enclosed basin, be it right in the deep Pacific, for example, today is sort of part of the lowest oxygen in the global ocean. And it means that things become marginalized, I suspect. And there you can find, in a way, this is house cyanobacteria, for example, have managed to keep this signal of low oxygen. You know, to me, it's always curious, why is it we see changes in the metals? They're living in the modern ocean today, but they're somehow preserving this kind of anoxic signal, often by living in those niches. Does that answer your question? It's a start, okay.
Great. Do we have any more questions?
Oh no, there's one
Sorry.
here.
Hello.
Hi.
Very interesting and memorable lecture from your good selves on this aspect.
Thank you.
My question is very simple, that life has always had a balancing act, it seems to me, always adjusting things to survive
Yes.
one way or the other. That's all.
Oh, okay. No, I think that's absolutely true. Yes, I think on many levels that's actually correct, yes.
I think that's a perfect note to end on. So thank you so much. Please join me in thanking you so much. And as part of Earth Science Week, we are having a photo entry where we'd like anyone who's an earth scientist who's in the audience to head out to our reception and give us a photo of themselves holding an I'm an earth scientist sign. So if we have any in the audience, please do take your photo and either email it to us or send it to us on social media for inclusion in a video later this year. Thank you again.
Good.
Oh, thanks for rolling with the pointer.
Oh, that's all right. It was one of those things, I just about had it figured out, but it did go.
I think the battery just,
Yeah, it
they
did
last
go.
about 43 minutes or something.
Really?
So,
Okay, thank you.
Iron is more cosmic abundance. It's stable.
Yeah, it's
From
got one of the
nuclear
best
physics,
nuclear
point of view.
energies, I know. Yeah.
And so things decay to iron.
Yes. It's kind of there on the energy well, isn't it? Yes.
So you